When we think of robotics, we picture silicon chips, printed circuit boards, and electrical currents. We assume that artificial motion requires digital code. Yet centuries before the Industrial Revolution, long before electricity was harnessed for power, a machine was designed to move independently, perfectly mimicking human motion. In 1495, Leonardo da Vinci conceptualized this mechanism. Operating without hidden strings or direct human manipulation, this was an autonomous humanoid knight driven entirely by internal physical forces. The entire system relied strictly on wood, brass, pulleys, and cables. There was absolutely no electrical or computing hardware involved. The existence of this design demonstrates that complex, sequential motion could be programmed using nothing more than physical variables and mathematical proportion. As an illegitimate son, Da Vinci was excluded from formal university education. Without access to the dogmatic, ancient texts of his era, he relied instead on direct empirical observation to understand the physical world. This technical drawing illustrates his first-hand dissections of human cadavers. Rather than using traditional medieval medicine, he analyzed the body as a complex biomechanical system. Bones were mapped as levers, joints as moving fulcrums, and muscles reduced to force-generating cables. By isolating these organic structures into what he called thread diagrams, he could mathematically calculate the exact vector of mechanical pull required to lift a biological limb. He was systematically reverse engineering the organic body. The human anatomy provided a direct physical blueprint for constructing artificial limbs. Translating biology into hardware presented an immediate problem, providing power and control to a machine using only stored potential energy. The solution began in 1478 with his design for a self-propelled cart. It utilized tightly coiled leaf springs hidden in drum casings, which functioned as a physical battery to store kinetic energy. This diagram shows the rocker arm escapement mechanism. As springs unwound, this teeter-totter device regulated gear rotation to prevent sudden acceleration. Above, rotating wooden cams struck specific levers to dictate steering, operating as physical read-only memory. This schematic details how he scaled up the cam programming for a mechanical lion in 1515. The system directed a multi-stage sequence, allowing the beast to walk, stop, and mechanically split open its chest to drop a cascade of lullies. By locking mathematical instructions into the tangible geometry of wood, Da Vinci successfully substituted human decision-making with physical variables. This exploded view of the 1495 mechanical knight integrates anatomy and programming. The lower body used a 3-degree of freedom system, where a central cable mirrored a biological tendon for standing. Above, an analog programmable drum controller inside the chest powered the arms. Through coordinated pulleys, the machine could stand, cross its arms, and open its jaw, while internal drums produced rhythmic sounds synchronized to its movements. Because the internal cables and pulleys were mapped precisely to human muscle groups, the machine's geometric proportions perfectly mirrored biological reality. For over 400 years, the complete picture of this engineering was obscured. In the 16th century, a sculptor named Pompeo Leone inherited the inventor's comprehensive notebooks. This demonstrates the result of Leone's arbitrary dismemberment of the volumes. He structurally separated the mechanical blueprints in Milan from their underlying anatomical logic in England. Without biological context, these drawings appeared as isolated machinery fragments, their engineering logic obscured for generations. It wasn't until the late 20th century that modern experts like roboticist Mark Rosheim reconstructed the physical prototypes. By mapping the isolated pulley systems to modern 3D models, they proved the 15th century geometry worked exactly as described. The kinematic designs uncovered in those codices were so precise that Rosheim explicitly used them as functional inspiration for modern robotic joints developed for NASA space exploration. The mechanical knight and the programmable cart were functional realities, their viability confirmed once the original engineering context was restored. In June 2026, an international consortium launched Leonardica 2.0, utilizing advanced computational matching to digitally reverse that 16th century mutilation. The digital restoration scanned the torn edges of parchment housed in Italy and computationally fused them with the corresponding anatomical fragments from London. researchers can finally view the unbroken translation from Renaissance thought into physical engineering, exactly as it existed on the workbench over 500 years ago. The true legacy of these designs lies in their methodology. Da Vinci demonstrated that biology, art, and physics are all speaking the exact same structural language.